Thanks everyone for coming to my talk today. I work on one of the teams that provides the recommendations for the Netflix service. And so working recommendations, I often get a lot of people asking me about recommendations for what they should watch on Netflix. What are the new great things to see, or what's the best movies that are there. And while I can kind of give some guidance, they're very biased by the types of movies and TV shows that I like. So I always feel a little guilty when I do that. But I think I'm happy here to talk about a subject I hope I can provide good recommendations about, which is how to build machine learning software for real production applications. And this is something that we've done a lot of work on at Netflix because we use machine learning deeply. And also something that even in my previous job at the labs, I did a lot of work. And I'm hoping that what you can do is really learn from the lessons and the problems we've encountered, and you don't have to run into these same problems too, and kind of can get things going in the right direction. And some of these might kind of be pretty straightforward, but I think they're very useful to kind of help to help you kind of build your software in a good way. So first, I'm just going to give kind of a background around kind of where Netflix is at right now, and particularly about the recommendations, because that's obviously where we have a lot of experience with our machine learning software. But I think a lot of the ideas translate to other machine learning applications as well. So when I talk about machine learning and Netflix, the first thing that usually comes to people's mind is the Netflix Prize. And the Netflix Prize was launched in 2006 to help to basically have people try to predict what people are going to rate movies on a 5-star scale. Now, back in 2006, Netflix is primarily known for shipping little red envelopes in the mail in the US. And so it was a very different product then. If we fast forward to 2016, a whole 10 years later, Netflix is now a global instant video streaming service. We've gone from just buying and shipping DVDs to even producing our own Emmy-winning content. And you can watch Netflix on pretty much any device that has a screen or can be connected to a screen. So as you can imagine, we've really changed a lot what we do in terms of machine learning, and it's much beyond just simple rating prediction. So what kind of scale does Netflix operate at now? We have over 80 million members. We're in over 190 countries, which is basically the entire world except for China. We're on over 1,000 different types of devices. People stream billions of hours of Netflix a month. We eat up over a third of peak downstream internet traffic in the US. And if you want to make sure that you're really getting the most out of your internet service provider, this week we launched a little tool called fast.com. You can go there and it'll tell you just how much of your bandwidth your ISP is really providing you by hitting the Netflix servers to see how fast the content's coming down. So in this new world, new scale, the goal of the recommendations has really changed from rating prediction to a more kind of holistic goal of helping members find the content that they're going to want to watch and that content that they're going to enjoy to increase their satisfaction with the product and with the content. And then ultimately, then if they are happy, they will retain with Netflix. And because we're a subscription company, we'll be happy because they'll pay for their subscription. And then we can go, again, buy more content, build better algorithms, make a better service. So what's our general approach to recommendations nowadays? Really, everything you see on your Netflix device across all different platforms is a recommendation. So this includes both the set of rows you see, things like dark comedies featuring a strong female lead, or because you watched House of Cards. How we pick those rows and order them on the page is done in a personalized way. In addition, how we rank all the videos on each row in the page and across the site in various ways is also done as a recommendation problem in a personalized way. So over 80% of what people watch on Netflix comes from the recommendations. And we've gotten to this point not just because we think machine learning and recommendations is cool, but we've found time and time again that it actually improves the user experience by improving how much time people spend watching Netflix and how long people stay customers. And then the reason I'm talking about this here, of course, is that the recommendations are totally driven by machine learning algorithms. So when I think about machine learning in the context of solving problems at Netflix, we really try to break it down into 5 different aspects. And when we work on them, we can really think about improving any of these aspects to make the algorithm better. And the first one is obviously the problem statement. What is exactly are you trying to predict? The old world, we might have focused on trying to predict ratings, but that's not actually maybe the best problem to go after. There's a lot of different subproblems we can tackle, and if we pick the right one that might be more useful or tweak how the definition of the problem we're going after, we can find that that's actually probably the most important thing you need to do when you try to build machine learning software. The second thing is once you figure out your problem, you want to go and make sure you find relevant data, right? So figuring out what features you're going to put in, how you're going to collect your labels and put them together. That's, again, super important to make sure you're going to have an effective system. From there, deciding what model you're going to train, what algorithm you're going to use to train it. And then once you've picked those, based on the data you've collected and then computed metrics, see how well it does. And then from there, iterate on all of these things and improve them over time. So machine learning for us is a very iterative process. It involves improving things on all of these different dimensions, not just, say, the models and algorithms that a lot of research and papers are written about. And we find that a lot of benefits can be found by changing the things kind of on the top part of the diagram versus the bottom. Of course, though, everyone wants to know about, oh yeah, but what are you guys using? What's that magic bullet that you found that solves or not that we solve recommendation, but that we use? And the reality is that there is no magic bullet. The real reason we basically use everything in the textbook, and the reason that these things are in textbooks is they're all very good algorithms for specific subproblems. So in different setups you have. So simple things like linear regressions, logistic regression, they have their great use cases. Things that we use a lot of matrix factorizations and extensions like SVDs, SVD++. We use other extensions to like factorization machines. In the neural network space, RBMs was something that was from the Netflix prize that we use. Deep neural networks, we also try using Markov model graph algorithms, clustering, LDA, ensemble forests, Gaussian processes. The list goes on. I think pretty much the only thing we don't use right now is SVMs. And being someone who really studied a lot of kernel stuff in grad school, that kind of makes me sad. But I'm sure we just haven't found that right perfect application for it yet. So when we try to think about taking all these models and putting them into production, there's a lot of design considerations you have to take into account, both on the side of the product, the recommendations, and then also on the software side. So we need our recommendations to be personal. I mean, we could throw in unpersonalized popularity, and that might do be better than random or alphabetical, but that's we can do a lot better than that. We particularly want to make recommendations accurate. So by using personal by using algorithms and personalizing, we can try to make very accurate guesses at what people want to watch and build and display those. But being accurate isn't enough. People have a wide variety of interests, and we need to make sure that we cover a diverse set of them when we're showing recommendations. So we can't just say, well, you watch comedies 90% of the time and documentaries 10%, so the most likely thing you're going to watch is comedies, we're going to show only those. You have to make sure that we balance the diversity of the person and also show the diversity of things that maybe they haven't expressed yet on the service. We also need recommendations to be novel. If we're just showing the same things you've already watched or very popular things that you've seen in other places, the recommendation system isn't very useful. So making sure that they're novel and help people find things that are new they wouldn't be able to find otherwise is very important. And finally, which is very important for the software side, is that recommendations have to be fresh. They have to be responsive to new actions and new data the user provides us, and also what's going on in the world around it, so that we can quickly respond to new events and new trends to keep the recommendations up to date, because still recommendations look really bad from a user perspective. On the software side, we have to deal with the scale we run at. So we run primarily in AWS, and that provides a lot of nice scaling capabilities, but we really need to be able to make sure we're running things that on a scale that works for the whole user base. We need to be responsive. So if we put something in the compute path, people are sitting there waiting for the recommendations to come back, so it needs to be able to happen really quickly. Because we run in the cloud, especially, it needs to be very resilient. So if systems will go down and we can't take down the whole Netflix site, we need to be able to handle failures in a graceful way. We have to be efficient because we are a business. We don't have infinite resources. So we want to make sure we're not wasting a lot of extra computation power that we don't need. And finally, we want to be flexible. So building machine learning is very iterative and requires a lot of research and trying things out. So making sure that the code and software is very flexible to support that is important. And of course, what we're looking for is that happy intersection where we can kind of meet both the needs of the software and the recommendation application. Luckily, we have a great software stack that we build on. As I mentioned, we run Netflix 100% in AWS. but we also have open sourced a lot of technologies on top of it. If you want to read about them, you can read it on the Netflix Tech blog. They describe a lot of them. But we run primarily in sort of a Java ecosystem in production, and that means that in the back end, we also tend to things like Spark and whatnot. So what are my recommendations? So the first recommendation is be flexible about where and when computation happens. So here's a blueprint of our system architecture. I'm not going to go into too much detail, but the main thing to see here is that we have kind of 3 different regimes: online, nearline, and offline, nearline, and online. So offline is where we typically do big batch processing, so we run our big machine learning algorithms, and we have things like Spark and Hadoop that we can use. Online is where we put things that are in the actual user request flow, so synchronous computation, that we have access to the most recent contextual data about what device people are on, what time of day requests are coming in. And then in between, we have this nearline system where we can update based on asynchronous events coming in. And this is a great place to put in things like online learning and then evaluating model parameters that are user-based. So to walk through kind of an example of how to take an algorithm and then think about breaking it up to be a place to get kind of the optimal performance we want in terms of these characteristics I mentioned earlier, I'll kind of walk through this example of matrix factorization. So for matrix factorization, we might start off with a sample matrix where you say collect sample of a big matrix of user by video data from the big play data archive that we have offline. We would then run some algorithm that would decompose that big matrix into a small user by factor matrix and another small item by factor matrix, of course with some regularization terms. And once we had done this big batch algorithm, what we do is we typically just throw away the user factors that we used in that sample and then only publish the video factors. And then in our nearline system, where we get events about someone has started or stopped watching a video, we then can take the item factors we have and then resolve to figure out the most fresh values for the user latent factors in the system. And once we do that, we can, in nearline, also compute the dot product of the user and item factor to get the set of recommendations for the user, and then store them in a reliable cache like EV cache, which is our layer on top of memcached. And then once the next request for the home page comes in, or we send a polling request back to have the device poll, we can, in the request loop, do any kind of contextual filtering we want, and then actually use that to serve up the final recommendations. Recommendation 2, design application software for experimentation. So I'm going to walk through an example development process that I've seen so many times, and I've seen I've heard a lot of people run into this problem in other companies. So typical thing happens, you have this great idea for a machine learning model, you go out, you find some data of how you're going to use it, you do a lot of offline modeling in your favorite language like R, MATLAB, Python, and you iterate a lot of time and you make your model perfect and you get that perfect final model that you want to put into production, you think is going to be amazing, and A/B test it. So then you start implementing it in the production system, and that world maybe lives in more Java or C++. And then you start finding problems. You find discrepancies in the data between the online and offline world. You find that, in the real online system, there was this post-processing logic you weren't taking into account when you were doing your experiments. You find performance issues in your code, and you find discrepancies between the online code and the offline code. So you spend a lot of time in these loops kind of debugging all these things. And it isn't until you finally resolve all of those that you finally actually see what the output of your model looks like in the production world. And it doesn't look like what you expected it to look based on your initial evaluation in the great model you had. So then you go back and try to figure out, was my idea wrong? Was there something messed up in the data? Was something in my code that needs to change? And so you spend a lot of time kind of trapped in these cycles, and each time you go back, you have to kind of potentially go through all these loops again. And so you can end up with a lot of time doing this. And so the solution we have kind of come up with at Netflix is to really make sure we share as much data, code and data as we can between production and experimentation, and really lean towards production. So make it so it's very easy to do things with the production system and the production code because, again, developing machine learning is iterative. So what we do is rather than trying to push the lab out to production, we try to take the application we're going to put this software in and really pull it back into the lab. Make that software so we can do machine learning on it and share as much as possible. And of course, you're never going to have that library that has everything in it already in your application. But you can do is make sure you have kind of very well-defined points for pulling things out and taking things back in. I thought that it ran into. Sorry. Yeah. Okay.
You're right.
Yeah. Okay. So having these well-defined formats can make sure that, again, that you maximize the amount of the existing code and minimize discrepancies as much as possible. And so it just helps you with this problem of avoiding dual dependencies. So when you have your experiment code, if you then make your copy of it that runs in production, and then there's a wall between the two, and there's typically even different people using it, and they iterate on it, it's very easy for these two things to get out of sync. So if instead you have a very big shared library that you use both for production and experimentation, and then the experimentation and production code themselves are really just the drivers of figuring out which parts I need to use to run my experiment, which parts I need to use to serve out production, it can eliminate a lot of these discrepancies and make it much easier for you to try your ideas on real data and real world scenarios to make sure you're going to have the maximum impact. And here, this means what do we put in the shared engine is pretty much everything we can. All the models, the features, the training algorithms, the metrics we have, et cetera. Recommendation 3 kind of goes along this line. Make your algorithms extensible and modular. So I think a lot of people, when they start getting started with machine learning, kind of go with kind of like the black box tools that are out there. So they have make it really easy for you to take your data and tweak a few parameters and get out something that you can do some prediction on. But what we find is that a lot of times those black box algorithms don't really work that well when we try them in our real problems and real production systems. And we spend a lot of our time really tailoring them to the problem domain that we have. And it's a pretty simple idea, but the thing to do here is that if you have these kind of black box things that are very hard to tweak, you spend a lot of time either rebuilding them or having to learn their internals and building very kind of brittle solutions. But if you're able to build kind of these white boxes where you have a lot of extension points where you can customize and tailor how algorithms work to your problem, it's become much easier to develop the algorithms you build on top of them. And in particular, when you do this, making sure you have really nice interfaces around the model and the algorithm itself so you can easily swap them in and them out and also do things like compose them together. And if you kind of apply this principle all the way down, what we find is when we're building software, we really try to provide good building blocks to build on top of. So we don't try to start from scratch. We try to build on build each of our algorithms kind of up in nice little units that we can always reuse kind of the next layer down if we find that something isn't working at the highest level. So starting from a good matrix library or linear algebra library that provides the good primitives that you want, like vectors and matrices, having good statistical tests, and distributions and things like that you can build on. Having abstractions for things like models, features, metrics, all the common terminology in machine learning. As well as in different domains, things like loss functions or things for optimization or abstractions for neural networks, et cetera. And then kind of at the highest level, that's where you kind of can build your domain-specific components. And sometimes you might you can just kind of plug in something to customize it. And then by using familiar concepts from the domain for the abstractions, really make it the job of the software to figure out how to put them together so you can express your idea in kind of the way that's most natural and leave the composition to a software engineering process. And so as an example, here is some code that from using an open source library I created with some people at Sandia before I joined Netflix. And we actually used parts of it within the Netflix system itself. So it's a Java library, so I apologize for the verbosity of the code. But the basic idea here is if we want to take something simple like a random forest and change how we're going to do the splitting criteria in the nodes to use some custom information we might know about the various features, the idea is you want to be able to take the code and be able to drop in my custom splitting criteria. I'm usually a very patient person, but for some reason with machine learning algorithms I get very impatient. So I really just want to see how this algorithm is going to perform after an hour to get the results. And of course, the metrics that kind of come baked into the algorithm are not what I actually want to compute things. I'm cared about things like diversity, so I want to plug in some custom performance reporting. And then at the end, when I'm done, I want to be able to inspect the whole thing and understand what's going on. And so by just providing all these extension points, you can make your libraries very flexible so you can tailor them for various different applications. Fourth recommendation, describe how your model, the input and output transformations for your data along with your model. So when we think about building software for machine learning, a lot of times what we're doing is we have some existing application, and the way I think about it is there's just some missing hole. There's some big problem in this application we need to solve, and the only way to solve it is using machine learning. So the question is, what do we put in that hole? So we go off and we build our great machine learning model, and we decide, okay, let's plug this in. And what we find out is that, well, that model we built, it typically requires some kind of, say, vector coming in that represents the data, and then vector out that represents the predictions. But then we go back to the people who built the application, and they're like, well, yeah, but the thing I have is the user, and the thing I want out is the set of recommendations. So how do I go from that to your internal vectors and whatnot, right? So the problem is that there's this gap between the two. We like to talk about features, and then there's but the application teams like to talk about real structured entities. So the question is this application code or model code? And it can be very natural to kind of drop in and say, well, the machine learning box is already there, so clearly it's application code. But what we found is that if we do this, it actually creates a very tight, brittle coupling between the two, and that really what fills in these gaps is really about, we think about as feature encoding, how you're doing this representation, and then output decoding. And those really are part of the machine learning algorithm, and part of the machine learning approach and the machine learning software. So it is much easier if you then describe how you're doing those things as part of your model instead of leaving that up to the application layer, and creates then a very nice interface and decoupling with the applications you put the machine learning into, because the application still gets to deal with its kind of high-level concepts and domain primitives, and then it's really part of the model description to figure out what to do with that, and that gives you tons of flexibility in the types of models that you plug in there. Just as a simple example of this, again, the recommendation domain, if we had when we have a system like this, we typically would have the high-level API be something simple like, here's the user and some videos and rank them for me. And then we can load in a model description that says, hey, I'm a ranker that scores videos individually. I have a set of features that I'm going to use, and maybe those features are parameterized. Then use, say, something like a simple linear model to score it. And by having this description, it's very flexible, and we can kind of plug in and out a lot of different ways of computing features, a lot of different algorithms. There are a lot of different models for doing scoring and whatnot. Recommendation 5. Maximize a single machine before you distribute your algorithms. So this is a common problem. You implement your software, your code, you get it working on a small scale, and now you need to scale it up on larger data, but it just, it doesn't work. So of course, you're working on this big data. You have these great, Spark, Hadoop tools out there. So hey, that solves scaling problems, right? But the reality is, like, really beyond trivial machine learning algorithms, scaling them is actually very hard, because there's typically a lot of communication overhead in them. And so often, if you want to scale an algorithm, you have to make a lot of changes and approximations to do it. So before you go there, I recommend just trying to squeeze as much as you can out of a single machine first. Memory, doing things on a single machine and communicating through memory has a lot more memory bandwidth than if you're trying to communicate over a network. And I think you'll be surprised just at how far a single machine can go. As an example, today Amazon announced this new instance type that has 2 terabytes of memory and 128 virtual CPUs. I don't know how many people are working on things where you actually, like, the binary memory representation is more than 2 terabytes. If you have more than that, then yes, you probably need to distribute it, but make sure you're really maxing out what you can do. And when you do that, first, do simple things like actually profile your code and think about memory cache layout. So here, small changes can have a very big impact. I've seen time and time again, someone transposes a matrix and it goes from something like, okay, this takes 100 milliseconds to this takes 3 milliseconds. So thinking through these things, you can, again, squeeze out tons of performance, even just out of just a simple CPU. And then once you get that working, it's very easy to typically go multi-core. So if you're doing SGD type methods, using things like hog-wild, which is just lock-free multi-core SGD, can work very well when you have a lot of data. And then also considering, hey, if you're doing things where it makes sense to use a GPU, or one of these, maybe someday soon, Google can release their new tensor processing units that they also announced this week. Squeeze as much as you can out of those, and then kind of go distributed. And then when you do distribute things, you can start with the outermost layers first. So for us, if we're trying to train models for different regions, start by separating out those problems and have those be distributed. And then for each model we're trying to train, we're going to want to make sure we have the right hyperparameters. So within one AWS regions, you'll distribute your grid search, or distribute how you're doing your Gaussian process hyperparameter optimization. And those are, again, super easy to distribute compared to the actual internal algorithms. So typically, this is kind of what the typical type of architecture we would land on for something like neural networks. But if we get to a scale where that doesn't work, then we would finally decide, okay, now let's actually try to tackle this as a distributed problem. But we find that very few, out of all the problems we have, very few of the ones we have actually need to get to that level. Recommendation 6, don't just rely on metrics for testing. So I see this temptation when people are developing machine learning software, which is that machine learning has this built-in testing process, which is that we use validation metrics to test things, right? We build our test, we have our holdout sets, we run our algorithms, we try them out. And so when you're building software and you kind of are doing it in this loop, you kind of said, oh, look, I put this in, the data came out, it's better. My software has to be correct, it has to work, it has to be great. And so that became very misleading because you can kind of feel like, oh, yeah, I'm doing great, doing great. But then the problem is when you hit this problem of like, oh, now the metrics didn't go up. Well, what went wrong? Was it the code? Was it my data? Was it the metric? Was it the idea was wrong? A lot of times people will just jump straight to the idea, or they'll spend a lot of time going back and they've written tons of code and they figure out what was that last thing I did and what was wrong. And it could be something very deep that's been in the code for a long time. And so I find the reality of testing is that machine learning code involves tons of intricate math and software, math and logic, in dealing with rounding issues in different corner cases. Just the simple thing between having a plus sign and a minus sign, where I've seen say the math someone derived or the paper they've been trying to implement had it wrong, can create totally different outputs. And again, it's not going to just crash on you. It's just could be just slightly off or slightly worse than you expect. And so the only real solution here is, I find, is just to really unit test things. And at first it feels like it's an overhead, but once you if you combine this with, again, building blocks, and you have good unit tested building blocks, you can have a lot more confidence in your software, and that means you can get a lot more things done in the long run. And I'll call it that testing your metric code is especially important. If there's like one thing to test, make sure is rock solid, it's your metric code, because that is what you're ultimately going to use as an arbiter for all the other decisions you're going to make. And the way I like to think about it is if you're working in a business, you're going to make business decisions based on the output of this metric. You're either going to say, hey, we should try this idea, or we shouldn't try this idea based on those metrics. So you want to make sure that those are really operating the way you expect and are very robust to various different corner cases. Of course, unit testing isn't enough. We're putting together, machine learning software, you're putting together large pieces, large chunks of code. You're dealing with real data. You want to make sure that that you actually have system level tests. And if you're kind of deploying the software, making sure at a minimum as you're developing that you aren't breaking the existing systems you have, doing some kind of checks across builds to make sure that the output stays the same when it's supposed to stay the same, I think is at least a minimum thing you should do. So that's in kind of my high level recommendations. I'll kind of come with a couple of final thoughts. So I really see machine learning as another way of solving computational problems, kind of in parallel to software development. Software development is something you do when you have a problem, you know the solution, and you can just write down the code and logic to solve it. And you kind of go through a typical process of you write your code, and then you compile it, you test it, you deploy it. This is kind of standard software engineering. And then when we do machine learning, we actually go through a very similar thing, but instead of saying, well, I don't know how to solve the problem, but I know I have this data that I could use to solve my problem. Here, rather than writing code, we kind of think about developing this algorithmic approach I was talking about earlier, the different areas. And then we, rather than compiling it, we train the code. Rather than testing it, again, we use our validation metrics. And then finally, we have this deployment step. which I think is an area where there's still very little work that has kind of been done. But I think when you think about these parallels, you kind of see some interesting things, which is that, again, if you focus a lot on the training algorithm, that's like being very obsessed with compilers when you're doing software development. And I think compilers are important, but the real important thing is, again, that how you develop that whole algorithmic approach is like when you write your code. And of course, when you're doing machine learning, each of these sub-steps does involve software development itself. So the takeaways for building machine learning software. So machine learning is an iterative process, so make experimentation easy. Take a holistic view of the application where you're placing machine learning. So don't think of just that one little box, but actually once you put machine learning into an application, that whole thing becomes a learning system, and you're going to want to apply machine learning principles to the whole thing. Design your algorithms to be modular. Look for the easy places to parallelize and optimize for a single machine first. And testing can be hard, but is worthwhile. That's it. We're hiring, so if you're interested, both on the machine learning and on the software side, so come talk to me. Time for questions. Yep.
I have a question. I work in also recommendations on hotel rooms, and so you said that you need to unit test, so that's of course a lot, but then you talked about full system tests. So
yeah.
For instance, one thing that we do is we push synthetic transactions and then check on the other side to get kind of relevant recommendations. Do we have any other kind of examples for like full system testing?
So the question is kind of for full system testing, kind of what techniques do we use? Yeah. So it can be hard. One of the things we've done is that we've actually built a system that will take the online microservices that our algorithms actually would kind of call to get all the data coming in, and we snapshot them so that we can kind of have very consistent views of like, this is what the data actually looks like when we get a request to do a computation. And so we can use that to kind of then feed through the rest of the system from the very outermost layer and see what happens through the whole thing. And we can do that to train models. We can also do that for basically full level system checks and putting large sets of components together and make sure that what comes out it looks as close, it looks exactly like it should in production, so that if we find regressions and issues, that we can detect them.
So once I do a limited data to make predictions, and content is so huge, so how do you take care of the input which you don't have and you don't might like it in terms of recommendation?
So the question is, we have a very limited set of inputs for the user, so what do we do in terms of recommendation?
I mean, let's say a new sort of content is coming to Netflix.
New sort of content. So for a new content, yeah.
Don't have enough data points.
So kind of the item cold start problem, new thing is coming, what do we do? So I mean, interestingly for us, for our domain, the item cold start problem isn't as big of a deal because we're not like doing news recommendation where things have a very short lifespan. Movies and TV shows, professionally created ones, have a very long lifespan. We license them for years. So, if on the first day we might have very little data. We do know things. We pay people to professionally tag the movies into various kind of micro genres and whatnot, like what mood it is, and what the profession of the main character is. We have all this metadata to kind of get things started, but from there we typically kind of just let the system kind of over a few days evolve to a stable state, and it doesn't take that long because we have a large member base, and so the algorithms can easily kind of pick up on it. But we do have some cold start features that we can use as well, like the metadata and whatnot. Over here.
When you talked about rewriting or rolling your own on a lot of different levels, you showed an example in Random Forest. What do you guys at Netflix find is the right level? Because presumably you're not rewriting your own gloss or CUDA, or you're not doing stuff in Fortran 77. So like how far? But of course you're writing your own application.
Yeah. I mean, that's good. So the question is, kind of how much of the code is custom and how much is kind of reused, and where do we draw that line?
And what's your decision-making?
What's your decision-making? Yeah. We try to use kind of as much things that are out there that make sense. Obviously, being on the JVM, that has certain limitations. Of course, the the library I showed earlier, the Foundry, it actually, it calls through to things that when you have BLOS and LAPACK installed and the native, library is compiled, it'll call straight through to the Fortran. So, at some level, we try to pull as much of those things up as possible and make sure we reuse all of that goodness. But when we decide, it's really we have to look at, how easy would it take for us to take this, software as it is and plug it into our system versus how hard is it for us to build it ourselves. And for some things, on the back end, it can be very easy to plug things in to kind of try out lots of ideas. And so we try to make it very easy to kind of get data out of our system, try out an idea, and then kind of bring it back in. But in the online world, it can be a lot harder because we kind of we want to make sure it runs at scale and is very robust. So that's typically where we might run some of our own. Or when the other thing is, if you have something again that's very textbook, there's probably a solution out there. If it's something that's very custom, very tailored, we want to build it ourselves, but we want to not have to build it from scratch. We want to build it on top of a kind of a good set of things that we already have. Yeah.
You talked about productionizing models, sealing it up, and then sending it out.
Yeah.
Are there situations where this sounds like very offline training situation? Are there situations where you're doing more online training where you can't actually productionize this model? It's doing something, it's being retrained out there live.
So I think if you're doing in a case like that, if you're doing live retraining, I think you'd have a similar problem you want to solve. It's just about having if you're doing online learning, having that feature description with your model means that again you can publish, say, your initial seed model, and then if you want to update it, you have again the full description of the set of features you need to train it. If you were to do it, you probably want to also publish. You might be able to publish even what the algorithm you want to use to train it, and again make that very modular so you can plug it in. So I think for online learning it works the same way, and it's really about how the data comes into the system and making that interface really straightforward. Yep.
You talked about what are the key metrics that you try to capture and how do you testing of those metrics? And at what level? Like each row, your recommendation?
Sure. So the question is basically what do we look at in our A/B tests? So the primary metric we care about in A/B testing is retention. Ultimately, like that, for us, we're a subscription company. Like I said before, if people, retention means people pay us, money at the end of the month. And so if we can move that, that means we've definitely done benefit to our business. And we find, again, with the recommendations, they move retention. That's the reason we do it so much. Retention, though, is hard to move. It's once people kind of are subscribed for a long time, they typically, if you've been to Netflix for 6 months, going to the 7th one is pretty likely. So we also look at as things that are correlated with retention, like how many hours of Netflix you stream. So that's a little more sensitive. And then we also look then if we're kind of working in different areas, looking down then at the kind of for each area metric of saying if you're going in, you're changing an algorithm in search, you want to make sure the search metrics are improving and not going down from your change and those types of things. But the primary drivers are kind of what we think of as retention and then streaming hours. Yep.
And a really related question may be you slightly pleased by results because I take my personal example. I hate the system. If I can disable it, I will do. Because most of the time when that things I will move names outside and search for exact name. So probably that UI don't let user quality in different ways. They give you wrong response.
So I'm trying to understand the question exactly. So the question is kind of, if you're doing A/B testing.
Retention and
yeah.
user satisfaction. What I mean, what user interface don't allow anything but always suggest recommendations. Make it to pierce the system so you got wrong results.
So you're saying because we already have a recommendation system, is there a bias that would make it such that if we took it away that that might actually come out better in A/B tests?
Maybe.
Like that, maybe?
I don't know.
So again, the way we got there was through A/B testing of, I've seen kind of time and time again when we've gone into an area that's not personalized, right? And we personalize it, it's better, right? If we go an algorithm without an algorithm and then we put in something, it's better. I'll give you an example. One of the recent things we kind of announced was that we actually trying to optimize the images we show people. So the kind of the box art representation on the homepage, for House of Cards, we could show a lot of different images that say House of Cards. And what we can do is actually try to optimize those, and we can find better ones. And again, we A/B test that, and again, we see meaningful results from that, such that we're willing to go and talk with the studios and get better images and try out lots of them to find good ones. So going to a very deep level with these algorithms and personalization is just even beyond kind of traditional recommendation. We just see time and time again, you can make the user experience better once you collect relevant data and can use it effectively. Any last questions?
Thank you.
Thanks.